Very nice job, and I will hand the remaining time to Alberto for next session. Thank you.
All right. Thanks for staying for the last session. This is the last spotlight session. We have really good work to be presented here, so I recommend that you shake your arms, shake your heads, slap you on the face if it's necessary so that you're awake. Without waiting more, I guess I'll just present the first speaker. The first talk will explain us how to deal with the insidious collision checking bottleneck by exploiting a very interesting family of curves. And the work is presented by Andrew Patterson, co-authored by Arun Lakshmanan, Benazio Chichela, and Naira Hobakimian.
Hello, I am Andrew Patterson from the University of Illinois at Urbana-Champaign, and today I will be talking about proximity queries for absolutely continuous parametric curves. In motion planning problems for autonomous robots, such as self-driving cars, the robot must ensure that its planned trajectory is not in close proximity to obstacles in the environment. However, the problem of evaluating proximity in general is non-convex and serves as a significant computational bottleneck for motion planning algorithms. For example, in sampling-based planning methods, nearly 50% of the runtime is expended in performing collision checks as shown in the top figure. In order to lower computational loads in real-time implementations, collision checks are performed only at discrete intervals along the planned trajectory, and which may incorrectly validate infeasible trajectories as shown in the bottom picture. In this paper, we present 3 methods. One, which calculates minimum separation distance between a planned trajectory and an obstacle. 2, which is tolerance verification to ensure the robot is some safety distance away from the obstacle. And 3, collision detection, which simply checks if the geometry of the planned trajectory intersects with an obstacle. A main feature of the proposed algorithm is their ability to provide proximity queries for a large class of parametric curves, more general than the ones that have been previously discussed. For example, we have parameterizations for trajectories such as Dubin's curves, Bezier curves, Euler spirals, and many others. Let's take a look at how the minimum distance between a convex polytope and this parametric curve is calculated. The procedure begins with the construction of an ellipsoidal convex hull that encloses the entire parametric curve and computing the minimum distance from the obstacle to the ellipsoid. Next, the algorithm repeatedly constructs smaller and smaller ellipsoids from the one most likely to obtain a solution following a branch and bound-like algorithm. If we only desire to query the tolerance verification or collision detection method, the algorithm will terminate after the first few iterations. Otherwise, we continue until a reasonable numerical tolerance is achieved. The novelty of this paper lies in the efficient construction of the ellipsoidal bounding regions based on the arc length of the curve. However, in general, the arc length is not of closed form computable for many of these parametric curves, so we introduce an upper bound on the arc length as shown. This lets us efficiently compute an upper and lower bound on minimum distance. Our algorithm uses these bounds to keep track of the value of the solution. The benchmark comparisons show significant improvements against Chang et al. In a method solely computing proximity queries for Bezier curves. The tolerance verification and collision detection queries only require tens of microseconds. Additionally, this method uses significantly fewer memory resources. Here are some examples where we compute the minimum separation distance between a variety of objects. These methods can be used to compute proximity between 2 curves or between a curve and a convex polytope as shown. In this stochastic motion planning example, we apply our methods to very quickly sample 1,000 collision-free Dubin's paths around 2 obstacles. We are able to achieve a runtime of less than 10 milliseconds per iteration on a single thread of a laptop CPU. We'd like to thank NSF-NRI, NASA, AFOSR, and ONR for funding support. Our code implementation in Julia is freely available on GitHub. For more information, visit us at the poster session. Thank you for listening.
Thanks, Andrew. The next talk will explain the consequences of the choices we make on representing orientations and their ability to learn forward kinematics. The work is presented by Reinhard Grassmann and co-authored by Jessica Burgner-Kars.
Okay, servus. This is on the merits of joint space and orientation representation in learning the forward kinematics in the special Euclidean space. So my name is Reinhard Grassmann. I'm with the Continuum Robotics Lab, which was recently moved to Toronto. So let me show you one of our cool robots. This is a tubular continuum robot. It has 3 tubes, which are pre-curved and super elastic. So each tube you can translate and rotate respective to each other. So it's really small in terms of diameter, and also the robot is quite compliant. And furthermore, you can achieve tentacle-like motion. As you can imagine from this video, the forward kinematic of such a robot is characterized by the highly nonlinear behavior and interaction between the tubes. So our question is, what are the right or good representation for the artificial neural network? So let me show you one toy example. In this toy example, we have 2 tubes. So we already figured out in our previous work that the joint space can be divided into rotational joint space, which is here in our case torus, and into translational joint space, here showing us a parallelogram. So the translational joint space has this form due to the interdependency of the translational part showing on the right side. We can disentangle this representation by applying the affine transformation on the right side. So we come up with 2 additional joint space representation, and also we can apply the matrix. So now let's take a closer look to the task space. Here we consider position vectors in combination with different orientation representation. This includes quaternions, vector parameterization, and also the well-known Euler angle. We are not only consider one set of Euler angle, indeed we consider all 12 different set of Euler angles. So at the end, we have 6 different representations for the joint space and also 15 different representations for the task space. So there are lots of results in our paper, but let me highlight some of these results. Here you can see by transforming the joint space, you can achieve higher accuracy, and also the convergence is much faster. And if you apply quaternions, you can further reduce the error. So this is not only true for our kind of robot, which is, broadly speaking, really complex. This is also true for, let's say, low-dimensional application. In this case, we also apply this to forward kinematics for Stanford arm. So let me sum up my spotlight talk with 3 take-home messages. 1, use quaternions instead of Euler angles. 2, you should transform your input and output accordingly. And last but not least, this is also mandatory for low-dimensional application. So I'm looking forward to see you during the interactive session, and thank you for listening.
Thank you, Reinhard. The next talk will explain us a method to avoid our lower limb prosthesis from preventing us from tripping by using forward predictive modeling and reflexes. It's presented by Harmut Geyer and co-authored by Nitish Tate and Nadagopal Srinivasan.
Hello, everybody. As introduced, my name is Hartmut Geier, and I'm presenting this work on behalf of Nitish Tata and Nandagopa Srinivasan, both students in my lab who could not be here today. The work is about powered prosthetic systems. These are mechatronic legs that have motors to drive the knee and the ankle joint. Current control strategies for such active lower limb prostheses and orthoses use pre-planned motions, severely limiting mobility. Forget about all the advanced planning and control strategies you have heard about at this conference for UAVs or autonomous cars. No such thing exists for prostheses. State-of-the-art are controllers that track pre-planned knee and ankle joint motions without regard to either the human user intent or the environment, with fatal consequences such as quickly tripping. We combine state estimation, learning, and planning to try to overcome this limitation, and in this particular example, continuously adapt the prosthesis control to avoid tripping. For that, we first fuse sensor data to estimate the pose of a prosthetic limb relative to the ground based on an IMU and a laser rangefinder. In addition, we used a we estimated a subject's future hip motion continuously based on sparse Gaussian processes. The black line in this animation shows the actual trajectory. The red distribution is the joint distribution, and the blue one is the conditioned joint distribution. With those two elements, the current prosthesis pose and the predicted human hip motion, we combine them in a quadratic program solver to plan updated prosthesis ankle and knee trajectories that avoid tripping. In this particular animation, the black areas indicate trajectories that would lead to a trip, and green areas are okay. And instead of a blue, regular minimum jog trajectory, you see a red trajectory that continuously is updated. The resulting controller prevents trips when subjects try to force them by actively lowering the hip. In the video, you see a subject with the prosthesis control mounted, and he is actively lowering the hip to try to make this prosthesis trip. Yet the controller avoids these trips and safely plants the leg in swing. Compared to state-of-the-art control methods, the proposed control reduces the rate of tripping by about 68%. Specifically in the figure, you see the propensity for tripping characterized by the probability of the knee flexion angle at landing. A large flexion angle indicates you're landing like this and have tripped. A small flexion angle indicates you're landing with a straight leg and everything went well. And the proposed control has much more propensity to land with a straight leg angle. While this was just one example, in the big picture, this research is heading toward artificial limbs which continuously reason about and adapt their behavior to the user and the environment, similar to what today you see in UAVs and autonomous cars. Thank you for your attention.
Thank you, Hartmut. The next talk is a journey into differentiable augmented Lagrangians to deal with very common nested optimization problems. The work is presented by Benoit Landry and is co-authored by Zachary Manchester and Marco Papone.
Hi, my name is Benoit Landry. I'm a PhD student with Professor Marco Pavone at Stanford University. This is also work done in collaboration with Professor Zachary Manchester, also at Stanford. We are interested in the problem of bilevel optimization. This is a class of optimization problem where the solution of an optimization problem is embedded either as a constraint or an objective of another optimization problem. We usually refer to the embedded one as the lower problem, and then the resulting one as the upper problem. And the reason now that we're excited about this class of problem is that if you start looking for them, you actually will find them all over robotics, from motion planning to estimation to machine learning. It also happens to be something that has a rich body of work in the operations research community. So our approach, we try to have an approach that's as general purpose as possible. And the way we do that is we develop a differentiable nonlinear optimization solver for the lower problem, and then we use an off-the-shelf solver for the upper problem. Now, without going into too much details about the inner solver algorithm, suffice to say that it's a combination of a first-order method, the method of multipliers, which is known to be more robust to initial guess, and then also combines that with a second-order method based on the sequential quadratic programming approach, which is known to have faster tail convergence. Now, building on that, one of the main design principle basically for algorithm is that it has to remain differentiable using automatic differentiation. And this is done through a lot of different decisions, for example, avoiding branching at all costs, also solving the KKT system in the SQP method in a specific way, or even choosing the right tools to implement the whole thing, in this case, Julia. So we were interested in applying in a broad range of problems. In this case, trajectory optimization in the context of in the presence of an external disturbance. So our system here is a 7 degrees of freedom robotic arm mounted with a flat plate on its end effector. The disturbance is some wind that is bounded essentially to be allowed to be stronger in the horizontal plane than a vertical plane. So looking at the bilevel structure of that problem, the upper problem in this case is simply the trajectory optimization problem that everyone is familiar with dynamics, but with the objective being the minimum worst disturbance that can be applied on the arm. Now, the lower problem in this case is essentially to maximize that external disturbance, which is applied to the end effector. Here we have some qualitative results of applying our approach to this problem. So on the right, you can see that, as expected, the solver finds a solution that essentially moves the plate more horizontal to the ground than it otherwise would, in order to avoid some potential strong horizontal wind, essentially. Now, we also applied the exact same solution method, but to a completely different problem. So in this case, we're looking at a parameter summation. So we want to recover the friction coefficient between this block and the ground after having pushed it. And so the bilevel structure of that problem is maybe a little less obvious, but it's actually still there. So in our case, the way we impose it is the upper problem is the dynamics residual from the observed trajectory, and then also with the parameter constraint. And our lower problem is actually the contact dynamics, which uses the nonlinear well-known complementarity constraint, as well as a Coulomb friction model. So with this approach, we can actually efficiently recover the parameters with some precision that's proportional essentially to the noise that we've induced in the system. But what we're mostly interested in is actually to see if it scales better in terms of computation time with respect to a method that wouldn't be exploiting this bilevel structure. And something that we're excited about is, even though we're still working on computation time, in terms of scaling, as you can see in the scale method, we scale significantly better than not exploiting that bilevel structure. So that's something we're very excited about. Our method is very general, and also seems to be scaling better than an alternative approach. Thank you.
Thanks, Benoit. And finally, last but not least, work looking at deep neural network architectures that are especially tailored to deal with the stochastic control problems by exploiting forward-backward SDEs. The work is presented by Ziyi Wang, and it's co-authored by Marcus Pereira, Ioannis Exarchos, and Evangelos Theodorou. All yours.
Hi, everyone. So today I'm going to present to you the deep forward-backward SDE controller. So, given a stochastic optimal control problem, we can apply the dynamic programming principle and obtain the Hamilton-Jacobi-Bellman PDE, which is nonlinear, and trying to solve the global optimal solution will suffer from the curse of dimensionality. But there are a couple ways to obtain a local optimal solution through approximation. And the first approach is linearization, where both the value function and the dynamics are linearized, and this gives rise to a family of gradient-based algorithms like ILQG, which is very common in the robotics community. We can also exponentiate the AJB PDE, which also makes it linear. And then under a certain assumption between noise and control authority, we can apply the linear Feynman-Kac lemma, which turns this linear PDE into a path integral. And this gives rise to the sampling-based path integral control algorithms. The third approach, which is also the focus of this presentation today, utilizes the nonlinear version of the Feynman-Kac lemma, which turns the HAB PDE into a set of forward-backward stochastic differential equations. The stochastic optimal control problem that we're interested in is minimizing the expected terminal state cost and the running state and control costs subject to some dynamics affine in control. And when there's no control constraint present, we simply use the quadratic control cost. But in many applications, we do deal with control constraint. And then when that's the case, we will incorporate a tanh function in our control cost function so that the resulting optimal control is clamped. Now let's go through the derivation with the flowchart. Given the HAB PDE, we can first rewrite it as a parabolic PDE. And then, applying the nonlinear Feynman-Kac lemma, we can turn this parabolic PDE into the FBSDE, where the backward process corresponds to the value function. And here, the forward process corresponds to the uncontrolled dynamics. And in most of the control tasks, the target state is simply very hard to reach with uncontrolled dynamics. So this calls for some form of important sampling to guide the forward sampling process for the FBSE system. And we can do so by applying the optimal control back into the forward process. But note that this has to be compensated for accordingly in the backward process. And we use deep learning to solve the FBSD problem. Given some initial state, we first randomly initialize the value function and its gradient. And then using the closed form solution for the optimal control, we can forward propagate the dynamics to the next state, which is then fed into a neural network for the prediction of the value function gradient at that state. We also forward propagate the value function using the backward SDE. We can forward propagate this until the end of the task horizon, where we can then construct the loss function using the propagated value function and the true value function at the terminal state using the terminal state cost. It's important to note here that we are now forward propagating a backward process, and we can do so by making the unknown initializations trainable and use the known terminal condition to enforce a valid initialization. We've tested it with two different network architectures. We first tried with the fully connected network at each time step for the prediction of the value function gradient. We've also experimented with using an LSTM and the same fully connected network across all time steps for the same prediction, and this resulted in many advantages. Most importantly, using the LSTM, we managed to get much shorter training time and much fewer trainable parameters. In terms of results, we've applied our controller in simulation on pendulum, carpal, and quadcopters, which are all very classic examples for optimal control. And for future work, we want to push our framework in two different directions. First, as a real-time MPC controller, and second, as a trajectory optimizer, which hopefully will also include some model learning component. Thank you very much. Please check us out at the poster.
Thank you, Ziggy. If I can ask all the speakers to come on stage for the Q&A session. And maybe you can stay in order so that we link numbers and papers to faces. Andrew, if you can come number one. Thank you. All right. Are there any questions?
Yep. This is for the first speaker. I thought that was really, really neat. I mean, collision checking is really hard. So you'd said something about keeping track of an upper bound. The lower bound was from the ellipsoids, but it was unclear what that upper bound was or how you were computing it.
So any point on the curve will be an upper bound for the minimum distance. Thank you.
Any more questions? If you can stand and maybe say your name.
Yeah, my name is Armin Orkanovic. I have a question for the fourth speaker. So regarding your example in your non-smooth dynamics, first question, how have you discretized this later for the optimization problem? And a follow-up question is, have you analyzed the interplay of the smoothing on the non-smooth dynamics and the discretization? Because essentially you simulate a very stiff system. Thanks.
So just to make sure I understand the question properly, you're referring to the estimation problem with the contact dynamics. Yeah, so in terms of discretization, this is discretized simply simpled over time. So I observe a trajectory that is simulated forward and then a simple state forward. In terms of smoothing those forces, I haven't necessarily done a comparison against like a smooth model. in terms of comparing what you would get if that would be different. But I suspect that it would be pretty similar. I don't think that necessarily there's a fundamental difference there. That's something we were actually, though, interested in, is that the fact that those smooth contact models might not have as much of like the bilevel structure. It is not as naturally obvious. But the hard contact models, which is the one that we use there, actually have that bilevel structure that I think we can, that is specifically well suited to kind of this approach. Not sure this answers your questions, but hopefully.
Just a short remark. But if you smoothen the lower optimization problem, you end up actually with a soft contact model. That was my point. And you have to have a fine discretization to resolve it. And have you investigated this interplay between the smoothing and the actual?
Sure. So I guess, but in terms of smoothing, so that depends. That depends on essentially how precise you are in solving the inner problem. So if you're finding a suboptimal problem, then I agree with you, some form of smooth model. I don't know that necessarily there's a clear physical interpretation of what kind of a suboptimal solution to the complementary constraints is. That's something that would be interesting to investigate, I think. But yeah, I think it's actually something that is instead interesting is the fact that having these soft contact models in terms of suboptimal lower problem are potentially more approximate, but definitely cheaper to compute efficiently. So there's something to be said about potentially maybe you just need a rough estimate of your parameter, in which case you solve the subproblem suboptimally, and then you can crank up that kind of the number of iteration you're doing in the inner problem as you need kind of more precision.
Hi, this is a question for the last speaker. Thanks a lot for the talk, it was very interesting. Can you talk a little bit more about the importance sampling step? And also, do you have any intuition as to how your solutions will compare to things like ILQG and path controls?
Yes, thank you for your question. So that's a very good question. So for the importance sampling step, the intuition behind that is that we want to now modify our forward process, but at the same time trying to make sure that we're still solving the same PDE as the original uncontrolled system. So I can talk a little bit more to you about the derivation of the whole process, but essentially somewhere in the derivation, you'll see that if you compensate for the backward process accordingly, which is essentially multiplying your change by the sigma matrix, your noise variance matrix, you essentially still maintain the original PDE that you're trying to solve. So that even though you're solving for an important sampled set of systems, you're still solving the original problem. And then in terms of the second part on the comparison, we haven't really done any comparison as of yet because our framework is because we're still only focusing on trying to push our framework to more general systems and then on real-time applications. So hopefully we can get some comparisons once we get there. Or we're also thinking of including some comparisons in future work in simulation first.
This question is about the first author, about proximity queries. So I got two questions, actually. The first one is whether the method is only designed for point robots or for arbitrary geometry of the robots. And second one is it only for 2D planes or for arbitrary configuration spaces?
Thank you for your question. So I'll answer the second one first. So far, we've been doing 1-dimension, 2-dimension, 3-dimension Euclidean space. Extending the results to arbitrary manifolds is something we haven't done in any specific case yet. Thank you.
Sorry. How about the first question about arbitrary geometry of the robot?
Right, so if I have a configuration space and maybe like a rotational space, it would be like SO2 or SO1, right? So that's a different manifold and would require a different set of mathematical setup. So we haven't done that yet.
Any other questions? Is Marco Pavone in the room? So Marco Pavone was the co-host of the session, and we agreed that if we ran out of questions, he would come out on stage and explain a joke. No, just No, just kidding. Maybe I'll just give an opportunity to any of you, whoever you want, to talk about the laundry list, like when things fail, or what are the limitations of what you propose today, if anyone wants to take on that.
Sure. I think maybe that way I can actually maybe answer a little bit better also the question that was asked me. I think something that's important is that because we have to kind of make the inner solver very bare bone, we still want to solve to optimality in order to recover these hard contacts that you're talking about. We have to do a lot of iteration of the inner solver. We can't necessarily check for convergence. So that's something that's definitely that we kind of need to figure out. So right now it's basically like a very conservative way of solving the inner problem because you have to do potentially a lot of iteration. And that's also why our computation time is still something that we're working on. But we think that's kind of an awesome avenue to explore, and we're excited about things that we can do in that area.
I thank you for your two questions, and those are two things we're very interested in working on. One of the things that's central to our method is we have an ellipse that bounds our function, and when you start putting this on other manifolds, what is the area in which you can move, if you imagine a string between 2 points? What does that mean on a different manifold, or even in 3 dimensions, if instead of just a one-dimensional line, you have some surface? Now you have to start talking about an ellipse with multiple foci that maybe bound a cloth deflection. So these are the things we're currently working on.
Okay, so obviously for our framework, as with all the deep learning related work before that wants to be applied in real time, there's still a long way to go for making this real time because we're training neural networks online over a very long time horizon. So, so hopefully this will also answer a previous question a little bit better. One of the direction that we're trying to do is definitely trying to optimize our algorithm a little bit better, looking into different network architectures, essentially play with different parameters to speed up our algorithm. And then that's why we don't have explicit comparisons with existing frameworks right now, because let's be honest, the existing stochastic optimal control algorithms are already really good, and they run very, very fast. So it's going to be very hard to compete with them. So that's why on the second part, we're also trying to utilize the advantage of our framework, which is that it's very general. So we're trying to solve problems that traditional stochastic optimal control problems fail. So that's the second direction that we try to push our framework into.
By the way, I don't have a timer here, so I don't know if we're over time or not. So we are? Okay, so thank you very much. Oh, unless, one second. I think there's someone that wants to say something.
Yeah.
Sorry. Yeah.
Okay, my work, it's empirical study, so it would be cool when if you have a kind of proof that none of the NNN can approximate, let's say, it's the Euclidean, special Euclidean space. And I have some clue why, but no proof right now.
Okay. Yep. You want a chance?
Well, I'm not doing optimization, so it's good. But I'll turn it around and say, like, applying these techniques to assistive devices, assistive robotics, is a great opportunity to improve the mobility for people who depend on legged assistance to regain, retrain, or rehabilitate locomotion capabilities. And working with humans, there's lots of things to discover and wonder about. It's much more complicated.
Thank you. So a big round of applause for our speakers.